Am I audible? Yeah. Right. So about 2/3 of you are here. But nonetheless, it's line 11, so we'll start. So how was MPI yesterday? Got a little bit of feel of programming? So we'll dig a bit depth of, so I got some questions on mail, how does this happen? And some of you were asking yesterday, so I'll try to clarify some of that. Right? But let's get started with something very simple to understand if you have gotten the grasp of it. So these are 3 processes, okay? We'll call them 3 MPI processes, okay? I haven't mentioned the rank, but you can say rank 0, rank 1, rank 2, right? So what is going to be the output of these 3 ranks? Someone who wants to answer, please raise your hand. Very simple. What is the output of each of the ranks? Simple code, right? X initializations and then increment and then print. So is there going to be some race condition? What are they going to print? Pardon? Yes, each of them are different MPI processes. And you can take this mic so that I can hear you loud and clear. Each of these are 3 MPI processes. That's the only information I'm giving you. So anyone who wants the mic, please ask Tushar. Yes, what is rank 0 going to print? So this rank, the first rank, rank 0. What is it going to print? 2 and 2. Okay, rank 1, 2 and 4. Are you sure? Okay. Rank 2, 4 and 5. So there is no race condition. Why? Because? They are private variables. Have we talked about private variables in the context of MPI? Local variables. We will say local variables to each process. They do not share the memory address space. They have distinct address space. This is the most important thing that you should remember. Okay? No matter they are working on the same variables, but they are working locally. If they want to propagate their data to some other process, they have to communicate. So MPI works on explicit communication. Okay? This is slightly different from OpenMP. All right. So yesterday we saw that we have different processes. But, and you write something like this, MPI exec. We haven't seen this yesterday, but let's just assume that this is a way to spawn these processes on 4 hosts. Yesterday we were running on just 1 host. So if you want to run on 4 hosts, we'll spawn the processes in this fashion. Okay? So let's say we have, so this should be probably minus and 8, but anyways, so we are spawning some number of processes on each of the hosts. So the question yesterday was, how are the processes being spawned, right? How does the process actually get spawned on different hosts? We are actually giving the command from one node. You log into one node, you can give the command, MPI exec minus N4. And the process manager takes care of spawning all these processes on all the other hosts. Okay? So there is something called launch node. Okay? So the node on which the Hydra actually is the main node from which you log in and you launch this job, we'll call this the launch node. And all these, the launch node, it spawns some proxy processes on the other nodes on which you want to run. So there are 4 hosts. So let's say host 1 is the launch node. The Hydra process manager, it first launches some proxy processes on the rest of the hosts. And these proxy processes will internally spawn any number of processes that you would have specified in the command line on each of these hosts. Okay? So that's how the internals of process manager, simplistic. So this is used in a open source MPI implementation, MPICH. We are not using that. We are using the Intel MPI. But Intel MPI also works on a wide range of process manager. It may use Hydra, it may use something else, in which case the working is slightly different, but this is the kind of the primary. All right, so, but they need to communicate, right? We have, yesterday we learned about one communicator, one global communicator. What was that called? MPI Com World. So many information needs to be exchanged, right? So every node, there is some key value stored through which some information is being exchanged, okay? Now, if you are communicating between two nodes, we will call that communication as you can communicate without point-to-point also. There's another way. But if we are communicating between two different nodes, you might have heard terms called inter, intra. So if there are two different nodes, we'll call it as internode, right? And if the communication is within a node, we'll call it intranode, okay? So this is some diagram. So some of you also asked resources. So there is no book, unfortunately, which explains all this. There are papers, they maintain a wiki page, okay? And you can look through the source code. For now, that's the state of the art of getting this information, but it's very useful. It's helpful to understand how this works, right? So this kind of shows, this is the launch node, and you have some proxy executables on each of the hosts, and then they spawn these MPI processes on the host. How do you spawn a process? How do you spawn a process? If you want to spawn another process from within a process, how do you do that? Fork, correct. So the same thing also happens here. All right. So you can see here, there are some, I was running some 8 processes, and I have specified some IP addresses of these hosts. And I have also said that you run, I have specified the IP address and the number of cores that they should use on each of the hosts. Okay. So on the launch node, there are some executables, some proxy executables, as well as the MPI processes, as well as on the compute nodes, there is the proxy executable, and there are the MPI processes. It was 8, so the number of processes spawned were 3, 3, and 2, okay, on each of these IP addresses or each of these hosts, okay. All right. So any questions so far? No questions? Okay. So, so some of you were asking yesterday that how does this error checking work, or does MPI correct all that? So MPI actually relies on the lower level interfaces, okay, for all the communication and correctness, transfer. So you might have read TCP/IP protocol, some of you, right? You're familiar with transmission, how network transmission happens, right? So MPI is slightly above that. It leverages everything that you have read in your networking course, okay? So we actually have someone coming from Mellanox who will talk more about networking in the context of HPC. Okay, so communication, just to recap, happens using sockets. We do not have to worry anything about that. MPI takes care of that. What do? We did point-to-point communication. We just said, send this data to this process. That's all. That's our job. Our job is to ensure writing correct code, right? Okay. So just a little bit more details. So typically, you may have some send queues and receive queues because you may be sending data to a lot of processes. Immediately, the data may not be sent. So it depends on the architecture, hardware, but typically there are some queues maintained. Okay. Also, if you are communicating within a node, sometimes for faster communication, they leverage shared memory. You have done shared memory programming, maybe, right? Using shared memory, how to, probably in OS course, right? So these are all optimizations. So we are not going to look into details into this. We'll look into MPI in more depth, okay? So can you please look through this code? Is this visible from the back? No? I don't know if I can increase it here. Yeah, no, they have not seen this particular code, but just let me see if I can zoom. Right, you can see better probably, right? Okay. So look at this logic, right? Forget initializations and finalization. Look at this logic. If my rank not equals 1, I am sending, and assume that I am using 2 processes. So basically this is rank 0 and this is rank 1. Okay. Sorry, let's say I am using 4 processes. Okay, so this is anything but rank 1 and this is rank 1. So is this code correct? So everyone other than rank 1 is sending 20 integers, right? So rank 1 should receive 20 integers from everyone else. You have done yesterday assignment. Rank 1 received from all the odd processes, right? Can you take a careful look at this code and tell me if there is any error that you can note? Who is, yeah, can you give the mic? Right. Right. Some of you actually did this yesterday and told me that it's not working. So it's your responsibility to ensure. This is going to compile fine, okay? It's a very subtle bug, okay? No debugger is probably going to give you the right answer. So you have to be very careful, right? So number of sends. You have sent from n-1 process, so your bounds should be correct, right?
Maybe you can repeat what he said. I'm not sure everybody got it.
Oh, did everyone get what was the error? Yeah, looks like everyone has got. Last row? Okay. All right. Okay. So that's why some challenges. You have to ensure it's all your responsibility that there are not some processes just waiting for data and there is no sender, right? So it will block. These are all blocking calls. We studied yesterday blocking calls, right? MPI send and receive are blocking. And then you have to ensure that number of sends, receives match. So avoid code that may lead to deadlock. So yesterday Sandeep had showed one code where, so he had send from process 0, send from process 1, receive at process 0, and receive at process 1. So this was fine, right? You all said that this is fine. But if you just interchange this, what will happen? Is this still fine or there's an issue? So this was fine. Now if I say receive and then I say send, is this fine? Basically, question is it going to lead to a deadlock or not? Yes, deadlock. Why? Who is going to wait? Which process? Process 0 or process 1? Process 0 is going to wait for something it needs. Come again. So it's going to send and then wait. Till what time? Or is it going to just wait forever? Forever. Why? Why is process 0 going to wait forever? Or is it going to wait forever? Previous one should be deadlock. Okay. So only one person is paying attention. Right? So previous one was deadlock in certain cases. Right? And in certain cases, it's not going to lead to deadlock. That I will explain later. Here, I have 0 send. There is no receiver. Receiver has, one is also calling send. Both are saying send. There is no receiver. So, both are going to wait for the other process to call receive. But the next example I showed was actually fine. Yeah? That's not going to lead to deadlock. Okay. So, with that, so there is something called eager versus rendezvous. Now, what I said was not completely correct. I told you that this is a deadlock. It's only going to be deadlock in certain cases. Though, you're not going to write the, so this is a, so we call it unsafe code. This may or may not lead to deadlock. It's going to lead to deadlock when your message size is large. Okay? Yesterday also Sandeep had told about this, that we have something called eager limit, which an optimization, implementations may or may not follow that. There's something called eager limit. I'll say that below 128 KB messages, for example, I'll copy to MPI buffer, or MPI will copy to its own buffer, which means the user is free to move forward. Okay? So user is not blocked. MPI send is not blocked in that case. Okay? In which case, the send and receive will not lead to deadlock. Is that clear? And then you have rendezvous when it doesn't copy, it's a large, it doesn't want to do an extra copy of large data, right? So it waits for the receive to be called, and only then both the processes will go forward. And so in this case, that send receive will lead to deadlock. Okay? So these things, sometimes we may not know, and sometimes you may write, okay, send, receive, and it's probably an incorrect code and it may work, and then when you increase the data size, it's suddenly not working. So this is one of the reasons. Like, yes. Yes, it's an environment variable, you can change it. Not hardware buffer. So this is an MPI. MPI is runtime. It's not in hardware. So you MPI, if the implementation has a limit, it will tell you that it's not possible, or it will override your whatever you have set. But it is possible to change at least till a certain point. You can easily change 128 KB to, let's say, 512 KB or so on. Okay, so what is the implication if I were to, let's say, I were sending let's just write safe code, right? Okay, so I was sending some 1 MB data and I'm receiving 1 MB data, okay? And my eager limit is 1 KB, okay? So it's going to wait for the receive to be called, which if I had set the eager limit to 1 MB, let's say, it's not going to wait. So what's the implication? Is there any performance difference in both? Yes? And what's the performance difference? Who was that? Which time? Transmission time will probably be the same because you are transmitting same amount of data. But end-to-end, probably communication time is more in which case? No, so we are discussing two cases. One in which my eager limit is 1 KB. Another in which my eager limit is actually 1 MB. So in which case you think performance degrades, and for sender or receiver or both?
Does it depend on one factor or two different factors?
You tell me. Do you have one factor in mind?
I have two in mind.
Yeah, tell me.
In the first case, you're looking at
First case is 1 KB, 1 MB, eager limit is 1 KB. Okay.
you're looking at 10 messages and acknowledgements, right?
Pardon? We are looking at?
Acknowledgements as well, right? Because the eager limit is smaller.
See, here we are not talking of acknowledgements at all. Both cases, we will have all the acknowledgements that typically takes place for message transmission. You can ignore that part. What else?
In that case, I think 1 MB would take more time.
This one, when the eager limit is set to 1 MB, it will take more time for the sender or receiver or both.
For the total.
Okay.
For receiver, essentially, communication.
So, you know, sender can call send here, okay, if this is my time, and receiver can call receive here. Correct? Now, after it calls, there is going to be some communication time. It kind of finishes here. Okay. So, ideally, I should say this is my communication time. So, sender is blocked in one case, in another case it's not blocked because I've changed the eager limit. So, is there a performance difference for end-to-end here, or is it only for sender, only for receiver?
Performance difference is only for the sender. But for the receiver, it will take the same amount of time because it's just receiving.
Right.
In the case of sender, it will like actually.
It's either blocked or not blocked, right? If you are sending something small, the sender is going to go forward. It's going to assume that data is sent. That is why, in this case, even if you had not called a receive, sender will actually go forward. Okay, the program is incorrect, and that is why, again, PAL program is hard. Okay, so you have to take special considerations for all this, that whether you are within eager limit, whether you are sending small data, large data, and whether you have matched sender receivers, and so on. And if you change the eager limit, will it affect your performance? It turns out it does affect in some cases, because the sender may be going forward, it may be doing some heavy computation. The receiver is not doing that computation, right? Okay. So, now we will bring one more thing into picture. We saw, so yesterday we were running on one host, right? So let's say these are my hosts, but the hosts are connected, right? Yesterday we ran on one host, we spawned all the processes on these hosts, on just this one host. Now today I am saying there's a way you can spawn multiple processes on multiple hosts, okay? Now these are connected, right? These are connected in some way. And the connection between the hosts is called, can anyone tell me? Pardon? Someone answered, I don't know who. Who? Yes? No. The network connection between all the hosts. Communicator is a software concept in MPI, right? So what I'm saying is, the connectivity between all the hosts. They are connected in some way, right? You have to connect the hosts in some way. Topology. It's called network topology. And that plays, it turns out that that plays a huge role in the performance. Okay? And I'll show you some demo for that. But for now, let's assume that we have this topology. What is this topology? What is this topology? Someone from this area. Ring. Okay, this can be a ring. You can consider this particular topology as ring. Or if it were something like this, then you would call it a mesh, right? Okay. So we have these ranks. Okay. So let's say we are just using one process per host or node. So we have 4 ranks, 0, 1 and 2, 3. Okay. So let's consider this as a mesh topology. And the ordering of the rank is XY ordering. Okay. 0, 1, 2, 3. So one observation that you can make here is the distance or the number of hops, we'll call it number of hops, or the distance between rank A and rank D, or rank D and rank C, and rank A and rank B. So pairwise distances are different, right? So does this affect our performance? If I was sending data from rank A to B, I would just incur 1 hop. A to D, I would just incur 2 hops, right? So does this affect our performance? If you say MPI send at rank A, and MPI receive at rank B, and MPI send at rank A, and MPI receive at rank D, right? So these 2 pairwise communication, will the performance be different? If it's blocking, it will be different. And if it's, what's the alternative? Non-blocking or? Okay, so I'm considering the end-to-end communication time. I'm not considering only the sender time, right? So what about the end-to-end communication time? So in these 2 cases, right, the first 2 cases, does it matter 1 and 2 hops? And if it does, in which cases is there case, can you differentiate, like certain cases it matters and certain cases it doesn't matter? Somebody wants to answer?
If there is some kind of synchronization between all the processes, for example, rank A was about to send data to all the processes, all the other processes, and then all the processes have to wait till they receive all the data, and then only they can. In that case, the second rank, the second communication that you mentioned might take longer, because of which process A, B, and C might be waiting.
Why would this take longer? So you are talking of a very different case, but still, you are saying A is sending messages to B, C, and D, and only in that case, A to D will take longer. Why? Because it's 2 hops. Just because it's 2 hops, or is there something else? So you are saying that if A was not sending to B and A was not sending to C, the time of A to B and A to D are same? No, I am telling a different use case. Let's say A is not broadcasting to everyone. Okay. Scenario 1, A is only sending to B. Scenario 2, A is only sending to D. Will T1 be equal to T2? Why? Distance. No, that's not true. Pardon? B doesn't act really as an intermediate node, so it's not copied all the way to B's memory or anything like that. It's all happens in hardware, so that's not an issue. Yeah, so you can assume that. So does number of hops matter always, is the question. No. Tell me about this topology. in this topology, what else matters? Is it just the hops? Hops equals to 1, hops equals to 2. Can I say that basically, so do you know how to calculate the time? I have it on my slide here, right? So you can calculate the time by, if I say this is rate R, okay? Data transfer rate R, and I am sending D. So are you saying that T1 is always less than T2? And is it like T1 equals half of T2? Last row. I'm giving you the bandwidth, R. Let's say the effective bandwidth here is R. And the data size, all the links, yes. All the links that we are concerned with is R. I'm concerned with A to B, A to D, right? And the bandwidth is R, data size is D, so T1 is D by R, right? That's the time, T1, and T2 is D by R as well. Right, so I am subsuming that in R. Let's say that's the effective bandwidth, including latency and bandwidth factor together, okay? It's not just the raw bandwidth. It does, but for now assume that it's same, right? Pardon? No, B is not, you mean in the first case? A to B? Okay, assume that A, B, D all are ready to receive, all are ready to send or receive, okay? There is no basically synchronization problem or any other issue. Yes?
The direction matters.
What matters?
The direction. If the link allows...
Let's say it's bidirectional link. Well, the answer is the data size also matters. Okay? If you are sending really small data, it probably is going to be about the same. If you are going to send really small data, you are probably going to see some effect of the latency here, which he pointed, because you have 2 hops. But if you are sending very large data, so in that case also, so the time not only depends on the hops and the data, it also depends on if there is some other traffic going on in the links. Okay, so that's congestion or contention. So let me quickly show some demos. I have set up some demo for this send receive. Okay. So let me first show the code. Okay, so this is a very simple code. I'm just sending 20 integers, right? And I will run it. So let me just use this time command. Okay, so this is 27 seconds. Now I will show you a second code where, okay, so this was to illustrate something else. Let me come back to this. Okay, so here I am going to send receive a large amount of data. So you see, in the first case, I had, actually I can do that here as well, 27 seconds, more or less the same. The data size didn't come into picture here. Only beyond a certain time, the bandwidth comes into picture. When you go from the latency bound region to bandwidth bound region, that's when your time will start making some difference. So now this host file this actually has, I have specified 4 cores on one node. Therefore, when I say minus N2, all the processes are on same node. Okay? They are not different hosts. Even though I have some 10 hosts here, because I have given a :4, I am saying that use 4 cores from that system. And when I say minus N2, it's going to use those 2 cores. Now, let me use a different host file. So, did you see the difference now? I'm sending the same amount of data. In the first case, I have 0.04 seconds. In the second case, I have 0.7 second. What's the difference between RR host and host file? I showed you a host file. And I said that both the processes are on the same node. Right. So when I don't specify any number of cores, it's going to round robin. Whatever number of processes you give, therefore, when I say minus N2, it's going to run on 1 and 2. And therefore, the network is going to come into picture. In fact, in this case, the topology of this particular system is something like this. So there is a switch here, and this is 1, and this is 2. This is actually 2 hops. Right? So you see quite a lot of difference between the first case and the second case. Okay? Now, just to illustrate one more point, let me show you first the. Okay, so this is the code. I am sending 20 integers, but I am receiving 10 integers. Is it okay? So is this code going to run fine? It turns out it's not going to run fine. So it's your responsibility to allocate as much as at least as much as data that you want to receive. Otherwise, you are going to get this error. Okay? It's okay to allocate 100 bytes. You can say that I am expecting 100 integers, but you're only getting 10 integers. That's fine. And yesterday, I think you have seen this, how to get the count. So you basically use a function called getCount. Yeah. So there's a function called getCount. You can query that to get actually how many elements have you received. Okay. And I have one last demo, and then we'll move on to a different topic. So here what we are doing is, we are, so multiple processes, it's the corrected code of the buggy code that I showed you. So only one rank is receiving, rank 1 is receiving from every other rank. Okay. So, you see, we have, okay, so let me just show you the other example, second example also. Okay, so again, you see the same difference, but there is another factor coming into play here. So in the first case, there were only 2 processes, one sender, one receiver. Here, we have 4 senders, 1 receive. When it was in the same host, it didn't matter much. When you went to different hosts, it has come to 1.2 second from 0.02 second, right? So one reason I already told you is they are on different hosts. What's the other reason in this particular example? Do you want to see the code again? Simple code, right? There are n-1 senders and 1 receiver. Right, very correct. Okay, so we'll pause the demo here and we'll move on to next topic, right? So our next topic is going to be collective communication. So we saw point-to-point communications, We saw a little bit of effect of data size, network congestion, and so on. So the other variety of communication is collective communication, where you're not calling a particular rank, but yes, you had a question?
Why are we using a mesh topology and not?
That's just an example. But star topology is very uncommon. Why? It's not scalable? Okay, maybe it's not scalable. And central point of failure, one point failure. If the central node is down, nobody is going to be connected to anyone else, right? This was just an example. These days you have many complex varieties of topologies. I don't want to go into the details of that because I have to cover collective communication now, okay? So, there are basically three types: synchronization, global communication, and global reduction, okay? But in this talk, I am just going to cover a very few, okay? So, MPI barrier. Yesterday you saw fence instruction, something like that, but this involves communication between all the processes, okay? So let's say all the processes are executing, and at some point you want that beyond this point nobody should go forward. I want all the processes to be at sync. In that case, you can call MPI barrier. But MPI barrier is a costly call, so you should not be just calling simply MPI barrier. What happens internally inside MPI barrier is, so there is an algorithm that runs. You have to communicate between all the processes, and everyone should know that everyone else has at least entered the MPI barrier call, okay? So this is typically what you may do: some compute, some communication, and then you may wait in certain codes, okay? So this is a common collective call, broadcast. So MPI bcast, this is the syntax. So in this broadcast call, we need a root process. That is, one process has the data and it wants to broadcast to everyone else, okay? So what could be a practical example of that? Can you think of a practical example when one process has the data and it's going to broadcast to everyone else? Maybe?
Security breach or something.
Security?
What group messaging on WhatsApp? If I need to replace like WhatsApp when someone sends a message.
Okay, WhatsApp maybe, in fact, using MPI broadcast. I don't know that. But yeah, yeah. They don't use broadcast, but that's a good strategy maybe to use. But it's not enough. You need to know. It's not only sending. You need to know that the process has actually, everyone else has actually reached that point. So you'll be probably doing some. So you're saying barrier implementation, you are sending unique tag to every other process? Who is sending? Barrier is like everyone should know. Pardon? Everyone is sending to everyone. That's a lot of messages going around. That's a very unoptimized implementation. They don't do that. But that's a, yeah, sure, that's one way to implement that. But say, for example, you have read a file. Process 0 has read a file. It wants to broadcast the content to everyone else. Or it wants to broadcast the minimum value to everyone else. Or it wants to broadcast something, the first element to everyone else, right? Okay. So this is the syntax. Now, question is, how do you implement broadcast? So I said that I have a message, okay? I have a message for all of you. How should I give the message to all of you? What are the different ways to do that? I should go to every point, right? I should go start there, and it's going to take me a long time actually, you know. I should put it in a common place and everyone else should rush to that place, and we just now saw some congestion effects, right? Not a good idea. Flooding, I should definitely don't do that. Right, I can delegate, I can have some. So we are not using binary tree, we'll use something similar, which is a binomial tree. Okay, so how does it look like? Okay, so basically, you can think something like this. If this was process 0, and this is say process P by 2 or something, okay? 0 can send the message to P by 2, and then what P by 2 will do? P by 2 should send to 3P by 4, correct. So when P by 2 is sending to 3P by 4, what should 0 do? 0 has already sent to P by 2. P by 4. Okay. Good. So you got the idea, right? You basically kind of conquer part of your domain. So I'll just send first to him message, then I'll send to him, and I'll kind of divide and conquer the whole space. So it's more efficient. Okay. So next is gather. To illustrate this, let's say we have, what is the default method? In broadcast. Yeah, what? Binomial tree. Okay, that's a complex answer, but so the implementations vary. The most commonly used open source implementation, they have 3 different algorithms for 3 different message sizes. Okay, I don't have the time to go into all the details, but this is the answer to your question. Okay, now gather. One more question. Okay.
If you want to broadcast one message to all the other processes, so even the other processes should be having a receive.
Okay. Let's go back to the, yeah. So I should clarify. This buffer, this is input at root and this output at all the other processes. This is where it's receiving. Okay. So if I can just pictorial draw. So let's say this is, so process 0, 1, 2, that's all. And 0 is broadcasting to everyone. So 0 has a buffer and it wants to send to 1 and 2. 1 is also going to have some buffer and 2 is also, but 0 has the data. Okay? When you say MPI broadcast, this buffer from 0, this data is going to be copied to here, this data is going to be copied to here. Everyone has that buffer array declared. It's just that it's input at the root process that is going to broadcast and its output at the other processes. Okay? Okay, that was a good question. And anyone else? All right, so coming to gather, right? So, well, syntax doesn't matter. Let's just look at the semantics. So, we have number of processes and we have some data. So let's say we have these are data. Okay. Gather also has a root. Okay. So now let's say root equals 0. So root equals 0, which means 0 will actually gather the data from 1, 2 and 3. So 0, at least 0 should have a buffer large enough to get the data from all the other processes. Okay, so this is what is gather. Okay, so can you think of an example where I can use gather or a combination of maybe broadcast and gather? And sure, give me some more concrete example. Sum of all elements. So how should we do that? How should we do sum of all elements using gather? What are the steps? So I'll tell you, so let's say I have a very large array, okay, and assume that I have somehow divided into all the processes, and I'll tell you how to divide, but for now let's just assume that I have part of this array and I am doing so what he said was, I am collecting the sum, right? So what are the steps? What are the MPI calls?
After the initialization, basically.
So let's say I have some valid data in all the processes, and this is process 0, and that is the root for MPI gather. So what should I call? You said sum of the entire array, right? So what should I call?
So you.
What should I first compute? And so assume that I have chunked,
Yeah.
right? So what should I first? What should be my first MPI call be?
Because that's what it does, basically.
I should gather all the elements.
Yeah, because. Okay.
So I wanted to do sum, right? So you are saying that I'll do all the computation at root process. That is one way, sure. I can gather all the sub-arrays into root process, and then root process will do the sum. Slightly more efficient way?
We can't guarantee.
Partial sums. We will first compute the partial sums, right? It saves us a lot of, it benefits us in a lot, more than one way. One is, what's the first thing? Why do you want to do partial sum? It will save the time because you're doing the computation in parallel. That's the whole point of why we are learning, trying to learn MPI, right? We have to do some computation in parallel. So assume billion elements and only 4 processes. We are saving a lot of time there. So let's say I have this local sum 1, local sum 2, local sum 3, and local sum 4, right? Now what's the next step? I have done the sum, those are the local sums. Now what do I do? Someone else. One of you 4? Just say anything that comes to mind. My goal is to compute the global sum, okay? I have billion elements. Expensive operation to do sum or maybe multiplication, whatever. I have the local sums in these 4 processes. I have taught you gather, where the 0 can get data from all the processes. How do I use that to compute the global sum? Yes, Meghal, right? Can you use the mic, please?
The 0 gets all the local sums and then we'll compute.
Then we'll compute the global sum, right? Now, what all does it save? One, you said that it saves the time. What else did it save? Sure, that is one point, very good point. We also saved on the communication time. We didn't have to communicate this large, big array. We just communicated one int or one double instead. That is what gather does, that's not your job. Yeah, so it actually does that. Okay, more details in my course, not here. All right, so we have saved computation time by computing in parallel. We have saved communication time by communicating just 4 bytes or 8 bytes. We have also saved some memory. We didn't have to copy unnecessarily to zeros memory. Okay, good. So we all know gather, and I'll show you one. So this is the exact demo I had, but anyway, so this is the syntax. It's not super important to remember the syntax, but you should know that you are So the send buffer, it's relevant at all the senders. The receive buffer is only relevant at the root process. Only root is receiving. And the receive count here is the count of elements that it's receiving from every process, not all together, but just from one process, how many count of elements. And count of elements here is important. So count of this type of data. This is not byte. If I say int, it should be like 4 ints. I'm not going to say 16 bytes there, okay? All right, and you should also note that we have a communicator here. Every collective communication call will have a communicator, okay? Zero needs to now divide just part of this array to itself and to 1, 2, and 3. It could have also broadcasted the entire array, but that's inefficient. A lot of unnecessary data in all the other processes. Instead, it will just divide and send just the relevant portion to the process. So, for that, we use a collective communication call called scatter, okay, MPI scatter. Okay. So, this is the syntax. Again, it's similar to gather. Okay, so let's move on at this point. There is something called all gather. It's just a variant of gather. In broadcast, you would have broadcasted the entire array to 1, 2, and 3. If you have n elements, you are sending n elements to 1, 2, and 3. In scatter, you are just sending n by 4 to each of the processes. So this count, send count, and receive count. So send count will be n by 4 in this case.
How do you write the data?
Automatically. So I have said that send, I'll give the starting address of the send buffer, and then I have already said that this is the send count and the send data type. So yes, scatter will take care of that. It needs to send from n by 4 or n by 2 or whatever. So you don't have to do anything further than that. Okay? Question? 2 questions, okay.
So my question is, once you scatter it and then maybe one of the processes has terminated, does it have like an automatic repeat request kind of
automatic repeat request?
As in basically, in case one of the processes has terminated, one of the destination processes has terminated.
The entire thing is going to crash. There's not much fault tolerance currently in MPI. Okay.
Ma'am, if one implements the scatter procedures using the MPI send, then will the runtime will be different in scatter and in those many MPI sends, or it will be equal?
Right. So this is a fantastic question. Can I defer that question? Yeah, I'll take up the question later. Okay. So everyone understood the question? The question was that, so I'm just scattering different parts of the array, right? And I also said that, so he asked me, wouldn't it be efficient to just gather step by step and then, pairwise gather and then do final gather? Yes, MPI does something like that, and I'm not going to cover more of that. But his question was, so scatter also similarly, MPI takes care of efficient implementation for scatter. It doesn't do send, right? So his question is, if I were to do send, it's the same thing, right? 0 is going send. It's the same thing, logically the same thing. What is the performance difference? So that's his question. I'll take that question later. All right. So this is a variant of gather. So in gather, what we did was, yeah, so I can use this. We had, so only 0 has all this, 4 local sums, right? L1, L2, L3, L4, Okay? All gather is everyone has all the sums, right? So not only 0, but everyone has these 4 local sums. That's it. Okay? All right. So just a simple illustration. There is another variant of gather. These are called vector variants. Okay? What it means is, here you had same number of elements, right? Let's say 5 elements. So let's say I have So in gather, you are necessarily required to have same number of elements being gathered at the root. But in gather V, what you can do is, you can just have, let's say, 2 elements here, and you can have 3 elements here, and so on and so forth. And you can have none from some process. So that is the vector variant, gather V. Okay? So that's why it becomes a little more complex than the call has a few more arguments, which is the displacement. Because 0 has to receive at the correct offset. If it's receiving 2 bytes from process 0, the next process, process 2, should come at +2 and not +4 or 5, whatever. Right? So that's why we have some extra arguments here. Displacements and anybody has a question?
Are these calls blocking? Like in
Yeah, these are blocking. These are blocking calls, but there is a difference here. So you said, so we saw this figure, right? 0 sends to 4, 0 sends to 2, 4 sends to 6, and so on and so forth. So this is broadcast, right? Once 2 has received, right? So in the next iteration, 0 sends to 1 and 2 sends to 3. Okay. So this is the complete iteration. Once someone has sent, okay, it can go forward based on what we just studied a few slides back. What was that? Eager limit. And so that process will not be blocked actually. There is no explicit barrier or anything at the end of these calls. So whichever process has finished, it will just go forward. But if you are sending a large message, some of these may be blocked if the receive is not called and so on and so forth. Right? Yes, all collective communication call. Same for everything. Yes.
Can we say that at the crux is some sort of dynamic point-to-point receiving?
Every collective communication call is implemented as point-to-point communications.
Can we say it's dynamic in nature because
Dynamic? What do you mean by
it doesn't
dynamic?
know the data size it's getting?
It doesn't know the data sizes.
That's what you told us, right? It doesn't know how much data.
When did I say it doesn't know the data size? Which one? So I should clarify. Which?
Gather
Gather V. No, it knows the data sizes, it's just not the same. Right? So you have to explicitly say that I am receiving 4 bytes from you have to explicitly, whichever process is doing the gather, right? So it should know that it's receiving 4 bytes from this process, 3 bytes and 10 bytes. It has to know. Yeah? Otherwise, the array will not be correct, the final array that it's gathering. Okay, any other question? Move forward? Okay. So, like I said, these are implemented as point-to-point calls. Okay? So, everyone else will send and the root process will do a receive. But this is just a simple implementation. It's much more efficient than this, I already told you it doesn't do one-to-one send receives. That is very inefficient. Okay. Next up, we have reduce calls. Okay. So what reduce does is, so let's go to the example. So you have some certain elements at all the processes, and you are saying that I want to find the maximum of each of these array indices, array elements, right? So pairwise across all the array indices, you are finding the maximum at the root. It can be anything. It can be one element, it can be n elements, anything. So you are doing a max. So these min, max, sum, prod, all these reduction operation can be done using this reduce call. So now going back to that global sum, we could use reduce also. Instead of doing gather and then a sum, we can just directly do a reduce. Right? Okay. So that's all I am going to cover on collective communication. Can't cover every collective call, but I think you got a essence, right? Flavor of what collective communications are. So next we'll take a look at a very important topic in PAL communication, right? PAL computing, which is scaling, scalability. How good is my code? You have heard these terms already, and Sandeep has told you about speed up. Yesterday we heard about speed ups. Now I'll talk about two terms or two measures that we typically see. So one is strong scaling, when your problem size is fixed and you want to increase the number of processes, but the problem size is fixed, which means data size per process is decreasing, because you're increasing the number of processes in the hope of doing less and less computation per process, because your data size is small, so number of computations you are doing is also probably small. However, there is a limit. Efficiency generally decreases in general. Why? Pardon? Overhead. What kinds of overhead are there?
Maybe gather overheads and
Gather. That's very specific. So you can just say communication overheads, right? One simple reason, right? There are other reasons. So often what is also studied is weak scaling, where you keep the problem size fixed per process. You do not decrease the problem size. You keep the problem size fixed as you increase the number of processes. So the amount of computation that you do is actually kind of similar, right? And the hope is that it's kind of going to be constant. So that's the hope of weak scaling. But again, there are overheads, and that's not the case. Okay? So let me show you some strong and weak scaling examples using. Okay, so I already have a script. Let me show you what I have in the script. Basically, I'm going to show you some scalability studies of one reduce code. Okay, let me show you the code as well. So this is simple reduce. I told you that you can use reduce to compute the global sum. That's all. And I have used a timer inside a code, so it's going to print the time as well. So now, okay, so I'm going to run this script. It'll take about a few seconds to run, because when you are using just two processes, data per two processes is pretty large, right? So I think there are about 1 billion elements, 1.6 billion elements. So you can see the time is reducing. And then what happened? You remember first lecture, Ashish said, time may actually increase. You saw this? Why? Overhead. And can you explain a little bit more? What else basically is happening? I have 1.6 billion elements. I am just doing a sum. First up, I have two processes. It took 1.7 seconds. 4 processes, 0.9. Pretty linear scaling, right? 0.5. 8 processes. And 16 processes gone back, 1.4. So what exactly happened? What is the reason? Can you just explain, other than just telling one Can you please take the mic?
Could you please scroll up so that we can...
Should I increase the font as well? Okay, I cannot, I think. You want to see the code? Oh, okay. Code is pretty simple. It's just reduce. Some local, some global, whatever we discussed, right? We do a local sum and then we do a global sum, that's all. But okay, so there's nothing much in the code. Let's look at the timings. 1.7, 0.9, 0.5 and then 1.4. Yes?
The MPI reduce, is it using the reduction algorithm?
What is the reduction algorithm?
It's a very common algorithm in the computer.
It's a very common algorithm. You have to tell me, I probably don't know it. So you have to tell me that. I can help you. So the reduction, the MPI reduce uses sort of binomial tree kind of algorithm for reduction, you can assume for now. Somebody wanted to answer? Yeah.
Maybe the work per process has been reduced too much.
Exactly. That is one good reason. I have now divided so much that my compute is very fast. These are gigaflops per second machines. Compute is very fast. I'm bottlenecked by the communication now. Right? Okay, thank you. So, now I will show you weak scaling. What is weak scaling? I just showed the slide before, but what is weak scaling? There is no divide equal, that's wrong. Keep the computation per process fixed, right? So, now if I run this, so I have, what I have done is, oh, let me show you let me show you the script first. So basically I have 2, 4, 8, 16, right? Per process, it has about 0.1 billion elements, okay? So this is weak scaling, right? So now let me run that. 0.2, 0.2, that's what I said. We will get linear scaling till a certain point again. Here as well, the same thing happens. 2 less to compute, and though the compute was the same, but we are bottlenecked by the communication. That's why you see this. Yeah, that's a very good question and complex question. That comes under the whole area of performance modeling. Okay? It's not an easy problem to solve. How much is the perfect size that I should give to a process to compute? It's right now, there is no known kind of algorithm that I can quickly give you, because the reason is, see, we are not, maybe if you are doing some summation, it's easy, probably. You can do some back of the envelope calculation on how many instructions and all is required for addition and so on. But my code is huge. Parallel codes are huge, right? To build that performance model is a massive task. That how much time it's going to take if I, instead of 1 megabyte, if I have 10 megabytes. Because it's going to affect your compute, your communication, all latency, bandwidth, everything is going to come into picture, right? But it's not impossible, of course, but it's a difficult task to do that, okay? All right, I have just one last topic. So not going into details, but there are non-blocking variants also, and this was recently introduced, recently in the sense MPI version 3. So currently we are in standard 3, so MPI 3 standard. So this was just introduced in the standard 3 version. Okay, so I'll show this during the demo, okay? But I wanted to cover one topic, which is, so we know the MPI COM world, we have one communicator. What if we want to split the communicator? So you can do so. You can split the communicator and you can do some, so these are like logical subsets, okay? So this is like intra-communicator, and if you want to communicate between this, then you will have to create an inter-communicator. Though by default there is MPI COM world as the global communicator, but any subsets if you want to communicate, that is inter, but here we are just considering intra-communicator, and this is how you do that. So if you have a communicator, which in our case by default, if you want to split the global communicator, we would have mentioned here MPI COM world. We will have to give some color key, and the new COM is the output. So for example, I say I am going to club everyone who is wearing a black cardigan, okay, into one group. Everyone who is wearing a blue cardigan into another group. So basically the split is by some color, and you, the programmer, has to assign the color. Every process has a color. The variable value of the color basically determines which group it's going to lie in. So let me show you one example. It will probably become clearer. Okay, so here we have some 20 processes, and I'm saying that I want to give one color to odd process and a different color to even process. So very simple. I should just do mod 2, right? The color should be rank mod 2, and I'll get 0 or 1. And then I can call MPI COM split. So here, actually I have not written that, but here you should call rank mod 2. Oh, here I have rank 3. So anyways, you can choose either mod 2 or mod 3, and then you have to call this COM split. So you get a new communicator. Now every process belongs to MPI COM world as well as a second set of communicator, right? But that's not same for all processes. So here, for example, if I had 9 ranks, then I would have actually 3 communicators, because I have said my rank mod 3 and I have 9 processes total, right? So if you do 0, 0 mod 3 is 0, 1 mod 3 is 1, 2 mod 3 is 2, 4 mod 3 is 1, 3 mod 3 is 0. So you get either 0, 1, 2, and depending on 0, 1, 2, you lie in either 0 bin or 1 bin or 2 bin. Basically the sub-communicators 0, 1, 2, right? So, and then if you do a COM rank and COM size, you have already seen these calls yesterday, COM rank and COM size. Now you are querying the new communicator. So then you will get the new rank and the new size. So here that is what is being output. The new rank is 0 for 0. It's also, so the 3 is of course common, because size for everyone, size is 3. 1 also gets 0 rank because it is the first rank basically in the second communicator, right? So 0, 1, 2, those are, you can say, the first ranks in each of these communicators, followed by 3, 4, 5, 6, 7, 8 and so on. Yes? Yes, I made 3 new sub-communicators. How do we access what? So we are doing a query on the new COM. New COM is the output. That communicator is of size 3 and my COM world was of size 9.
Is it possible for you to assign 0, 3 and 6 in one class and so on?
Yes, you just need to change the color.
Okay, but you're not doing mod there, right?
Yes, you will use something else maybe. Some function you have to use. Whichever way you want to assign the ranks, you have to use that function so that the same color gets assigned to 0, 3, 6.
Okay, and you can do it totally up to your...
Yeah, it's under your control. No, there are 3 communicators. So, again, parallel code. Yeah. Synchronization?
In the new communicator, is it?
No. So, see this this argument, third argument, I ignored the argument. So that determines kind of the rank that you will get. Since I have kept the rank as my rank, the current rank, the rank order doesn't change. It will again order from 0, 1, 2. Okay? So here, see, here 0 gets 0 rank, new rank of 0 is 0. It's the first process in that first subcommunicator. New rank of 3 is 1 because its order is slightly higher than 0 in the old communicator. So it gets 1. So again the numbering is contiguous. Yesterday we have seen 0, 1, 2, 3, n. So numbering is contiguous, has to be.
The Myran argument that we are passing on,
Yes.
that is aiding this.
That is the reason we are getting this rank because, so instead of my rank you can also say my rank plus 1. That is just a key. What it determines is the order of, the key determines that what is the order of 0, 3 and 6, the rank order. Okay.
So there are 3 communicators created here, 3 subcommunicators.
3 subcommunicators.
How do we identify each of them like from any other process?
Right. So one thing you have to understand, this is a parallel code. Okay. New com is relevant at all the processes, but new com is different for 036. 036 thinks that I belong to this new com, the same new com. Again 1, 4 and so on thinks that I belong to this. So that is taken care by the MPI runtime.
Now, like the folder if my rank is 0, then the 3 processes will be running that folder from the 3 different communities.
Absolutely. Not my rank, new rank. Did everyone understand the question? That was a good question. So if I say if new rank equals 0, again parallel code, right? Everyone executes that statement. New rank equal 0 in 3 processes. New rank equal 1 in 3 processes because we have 3 subcommunicators. So that was the question that I'll print 3 from 3 ranks. All the processes. No, new rank is 0 for 3 processes. Right? New rank is not unique across subcommunicators. It's only unique within a subcommunicator. Like the same thing, like rank is unique within com world, right? Yes, that's what subcommunicators have rank. No, processes have ranks. No, communicator for our context, no. MPI takes care of how it distinguishes between subcommunicator, sub-subcommunicator and so on. We cannot be saying rank, but we have the variable, the handle, communicator handle, that's all we can access.
So if you want to take the rank 1 process in a particular subcommunicator, then where you can query.
Yeah, so that's how you should use this color variable, right? Okay, one application of the collective calls that we learned in the first half. So the problem is to do matrix vector multiplication, right? So how should we, so what collective calls should we use basically? So let's say I am dividing so I have 3 processes and I have these rows and columns whatever per P1, P2 and P3. So what kind of collective calls shall we use? So assume that this part of the matrix is only with P1, this part of the matrix only with P2 and so on, and this part of the vector is also only with P1, P2 and P3. So in order to do the complete multiplications, additions and everything, so what are the communications? Scatter, gather are the only things we have learned, but what? I have to gather this vector. Where? All gathered. So everyone will get this vector because we need to multiply every row with this column. Okay. That's it? and then we have to gather the result. So this process will compute this much, this, and so then we will gather the result. Is that clear? Simple, right? Okay. So this is your assignment, one of the assignments, right? So that's all I wanted to show. So we'll get started with the hands-on.